Hi everybody! In this video we're going to talk in a little bit more detail about translations of both the vertical and horizontal variety. We saw a little bit of this in the last video, just a sampling, and now we're going to go into a bit more detail. So first, let's recall what a translation is. In the last video you'll remember that a translation just meant that every point of a graph was shifted by the same number of units, either up, down, left, or right. So we can say that a translation is a slide of a figure by the same number of units and in the same direction. So every point is either going 2 units to the left, or it's going 2 units up, or it's going 2 units at a 45-degree angle. We're only going to be interested in the ones that go directly up, directly down, directly to the left, and directly to the right. So let's see our first example. These are vertical shifts or vertical translations. This is the same example that we saw in the last video. The red graph is one of our parent functions. It's the graph of x cubed. The blue graph is a vertical shift upwards of the parent function by 2 units. This point, the focus, goes up by 2 units, so the new coordinates are 0, 2 instead of 0, 0. The orange graph is shifted down by 2 units, so instead of having the focus at 0, 0, now it's at 0, -2. Let's look at another set of points. The red graph, we have the point 1, 1. We can see this on the table. If we look at the table for x cubed, when we plug in 1, our output is 1. So the output tells us the y value. Now on the graph of the blue function, if we plug in 1, we get 1, 3. So here's the equation for the blue function, x cubed plus 2. When we plug in 1, we get 3, which is 2 bigger than the y value of the red graph. We add 2 onto it. So now, on the orange graph, when we plug in 1, we get, oops, where is it? Come on. Ah, it's not staying. Anyway, you plug in 1, you get -1. So what do you think the equation for the orange graph is? Well, actually I gave it to you. It's right here. X cubed minus 2. Each point, to get from the red graph to the orange graph, you subtract 2. I don't know why it's not working. Let me try to fix that. Show the table, perhaps that will help. Okay. When you plug in 2 into the orange graph, you get out 6. Which is 2 less than what you would get if you plugged in 2 for the red graph. So what we're seeing is 2 different kinds of vertical translations. Upwards gives the blue graph. In order to get the y value along the blue graph, you can plug in x into the red graph and then just add 2 onto it. Which is basically like saying take the equation of the red graph, which is x cubed, and add 2. So let's put that into this document as a rule. So if we have a graph, we have an equation g of x, and g of x is just the same as the equation for f of x with some constant added on, then the graph of g of x is a vertical translation of the graph of f of x by 2 units, or sorry, not 2, by c units. We just add 2 onto all the y values for the red graph. Let's remove these blue points now. Actually, let's put the blue graph away. Now, if we want to get a translation downward, we need to subtract that number of units from each y value. So we take the equation, x cubed, and we subtract 2. X cubed minus 2 gives us all of the outputs for the orange graph, all the y values to the orange graph. So let's write that rule in. If g of x equals f of x minus c, then the graph of g of x is a vertical translation of the graph of f of x by c units downward. Here, it was upwards. Okay, so if we want to move the graph in a vertical direction, we need to take a function and just add a constant on or subtract a constant from the entire function. To do shifts in the leftwards or rightwards direction, things are a little bit different. So let's see how that one works. I have way too many graphs here. We'll look at some more of them later. Okay, first let's just look at the graph of x squared, which is this red graph, and the graph of x minus 2 squared, which is this green graph. I think it's useful to look at the tables for these graphs. One thing you'll notice is that the green graph is definitely a shift to the right by 2 units of the red graph. We can see this from the focal point. If red has its focus at 0, 0, green has its focus 2 units to the right. So the x value changes by 2 units, and the y value stays the same. So this can get a little bit tricky. Let's look at another set of points. When I plug 2 into the red function, I get 2 squared, which is just 4. So 2 comma 4 is on the red graph. In order to get 4 on the green graph, I need to plug in, oops, let's see, if I plug in, well, this is actually the point I want. Come on. Let's try it mathematically. So if I want to get an output of 4 on the green graph, I need to plug in x equal to 4, because when I plug 4 in for x, I get 4 minus 2 squared. 2 squared equals 4. When I do 4 minus 2, quantity squared, it's like the function x squared. So hear me out one more time, because this can get a little bit tricky. The parent function is x squared. This is a shift to the right of the parent function by 2 units. So one way to think about it is, what do I need to do to my x values for the green function in order for me to just be doing the parent function? So since the green values are always the same, for the same y value, you need to go, your x value is 2 bigger, we sort of have to reverse that logic. We need to plug in something that's 2 smaller in for x, and that's the same as the original function, x squared. So let's write it down as a rule. That might make it a little bit easier to understand. So if g of x is the same as f of x, except instead of x, I plug in x minus c, then the graph of g of x is a horizontal translation of the graph of f of x by c units to the right. Phone's ringing. Let me close the door to not let it be distracting. Okay, so if we want to get a shift to the left, so say I want the graph to be here instead, well, I'm going to need to use x plus c instead of x minus c. So let's try that. Let's try to come up with a function that is the red graph shifted to the left, translated to the left by 3 units. Think for a moment about what you think it should be. It's going to be of the form x squared. But instead of x, I need to plug something else in. I need to use plus 3. And now you see that in order to get 4, like before, instead of plugging in 2, that's not going to work because 2 plus 3 squared is 25. I need to plug in -1. I need to plug in something that's 3 smaller. So if I add 3, it's like I was doing the original function x squared. So let's write that rule down. If g of x equals f of x plus c. So it's the same as f of x, except x is switched. Then the graph of g of x is a horizontal translation of the graph of f of x by c units to the left. So here's an example. Oops. For you to think about. What does the graph of, let's say, x minus 2 squared plus 3 look like? Well, the first question is, what's the parent function? The parent function is x squared, so this is going to be a shift of the x squared graph. The first thing I did is I switched x to x minus 2. So I switched x to x minus 2. This is going to be the graph of x squared with a horizontal translation by 2 units to the right. So let's see if we can get a little picture of this going. Sorry for the holdup. My technology is being quite slow. Okay. So, if I have the graph of x squared, it's a parabola. Now, what have I done? I first shifted 2 units to the right because I switched x minus x to x minus 2. So if I go 2 units to the right, 1, 2, the new vertex would be here. So this one is the graph of x minus 2 squared. But what else did I do? I added 3 onto the whole thing. By adding something onto the whole thing, you go several units upward. Here, in this case, it's 3 units upward. So if I go 1, 2, 3 upward, now I have this new parabola. This one is x minus 2 squared plus 3. I'll make a video with even more examples of these later, but hopefully this example helps you to understand what's going on. And let's get one more shot of the rules, in case you want to write that down. Good luck on the problems.